Why do some chemical reactions happen more quickly than others? Does adding more substances to a reaction always make the reaction bigger and better? Why is it important to follow a recipe when you are baking? These questions can be explored through one very important topic in chemistry, reaction rate. Hi, my name is Emily Berman, and I'm a science teacher in Pawtucket, Rhode Island. Think about the video you just watched of various chemical reactions. What did you notice about these reactions in the video? What did they have in common? In this Blossoms lesson, you will work to understand the factors that affect reaction rate through the analysis of a toy's design, the Alka Seltzer rocket. You will work using the same practices as scientists and engineers to determine the best design for an Alka Seltzer rocket based on your understanding of reaction rate. You will work together to create models of the chemical reaction that will create the best rocket on the macroscopic and microscopic level. This will help you better understand what conditions will make an improved rocket. Watch these rockets and notice what they have in common and what is different. Rocket number 1 has a whole tablet of Alka Seltzer in cold water. Rocket number 2 has a whole tablet of Alka Seltzer in hot water. Rocket number 3 has a broken tablet of Alka Seltzer in cold water, and rocket number 4 has a crushed tablet of Alka Seltzer in cold water. Now, you will start a classroom activity through which you will be guided by your teacher. We will look at data from these 4 Alka Seltzer rockets to work through this activity. Work with a partner to note your observations. Let's begin. Nice work! You just had a discussion with your partner about the patterns you noticed in the data on the handout. Hopefully you noticed that in data set 1, hot water reacted more quickly than cold water. It's important that you showed this some way in your model. In data set 2, you should have noticed that a crushed tablet reacted more quickly than a broken tablet or a whole tablet. You also needed to show this some way in your model. Now for the next steps. In the next class activity, your teacher will engage you all in a whole class discussion where you will have a chance to explain and share your models. You will also be able to talk to your peers about their own models and ask them questions. Secondly, you should have a whole class discussion to come to consensus and revise your model. After this, you will turn to your handout to write a CER paragraph. That's a paragraph with claim, evidence, and reasoning. You will write this paragraph so you can engage in argument from evidence based on your revised models. The CER paragraph should answer the question, what causes some rockets to react faster than others? Don't forget to incorporate data in the evidence section of your CER paragraph. Nice work. Now that you've all worked hard to think about what causes some reactions to happen faster than others, let's take time to learn about the factors that affect reaction rate. A reaction occurs because of a collision between molecules. The factors we will look at are concentration, temperature, and surface area. First, let's look at concentration. Concentration is how much solute, for example, Alka Seltzer, is present in relationship to the solvent, for example, water. Next, temperature. Temperature is defined as the average kinetic energy of molecules. Kinetic energy is the energy that an object has because of its motion. A high-speed molecule passes through more space per unit time than a low-speed one, so it has a higher chance of colliding with the reaction-creating molecule. And it turns out that a high-speed collision is more likely to create a reaction than a low-speed one. In summary, high temperatures mean high speeds, more collisions, and more reactions. After that, we have surface area. Surface area is connected to how much of a solute is exposed during a reaction. Now that you've been exposed to information about the factors that affect reaction rate, you're going to need to put your engineering hats on to complete 3 tasks. With your partner, you're first going to revise your models for a 3rd time to incorporate the new information you learned about the factors affecting reaction rate. After you do this, We will design an improved Alka Seltzer rocket that will react even more quickly than the rockets you saw in data tables 1 and 2. After you design this rocket, you'll have to explain your design. Finally, you're going to try to apply your knowledge to a similar situation by making predictions about rockets made by NASA. Your student handout will walk you through these steps. Amazing job today. Through this lesson, you worked hard to think about what causes some reactions to happen more quickly than others. You developed models to explain your thinking and argued from evidence to validate your explanations. You also acted as engineers today by designing an optimal Alka Seltzer rocket based on the new scientific information you learned. You thought about the different factors that affect reaction rate, and from this information designed an improved Alka Seltzer rocket. By analyzing data and developing models, you were able to use pattern recognition to design a solution. Hopefully from this, you notice that warmer water and a crushed tablet lead to a faster reaction rate. And after that, I hope that you were able to use these ideas to apply them to a larger scale, real-world problem. For example, these principles can be applied to everyday activities, such as baking, or larger problems, such as NASA's rockets. It will also come into play when you learn more about chemistry concepts, such as oxidation-reduction reactions. I hope you had fun today acting as an engineer. You use the actual science and engineering practices that real-world scientists and engineers use every day to ask questions, develop models, and design solutions to explain phenomena in our everyday lives. Congratulations. Thank you for considering using this lesson. This segment will just be a time for me to explain how to best approach this lesson if you decide to use it in your classroom. So it was designed to be aligned with the next generation science standards, specifically through engaging the students in the science and engineering practices, applying cross-cutting concepts, and understanding disciplinary core ideas. Specifically, understanding reaction rate is foundational in a chemistry classroom, and that's what we use to investigate a phenomenon in this lesson. So reaction rate is in next generation science standards in the standard HS-PS1-5. And that standard is apply scientific principles and evidence to provide an explanation about the effects of changing the temperature or concentration of the reacting particles on the rate at which a reaction occurs. So, understanding reaction rate on both a macroscopic and a microscopic level will help students better understand everyday activities such as cooking and baking, and also help them later on in chemistry with more complicated topics such as an oxidation reduction reaction. So this is supposed to be used sort of as an introductory lesson to all of this. So in this lesson, students engage in an inquiry project, and through this, they're able to be autonomous, creative, and they're able to collaborate with their peers. Students also learn a foundational chemistry topic that will apply to the world outside of the classroom. In addition, I really like this lesson because it engages students in discussion and discourse, specifically through arguing from evidence on their handout and in a whole class discussion. So by developing this phenomenon, that Alka Seltzer rocket, it's developed into a way to engage students in the engineering and design cycle, so they'll have a richer and deeper understanding of reaction rate. Also, this lesson offers a reflective experience on the importance of developing, using, and revising models and conducting investigations to collect data and test hypotheses. From the teacher perspective, I like this lesson a lot because it's low cost, it's student-centered, and it moves students from traditional step-by-step experiments to engaging in engineering practices. So, Before you start this lesson, students should have some understanding of how to visualize molecules and atoms on the microscopic level. This could take on practicing drawing these things in other activities, or just coming to an understanding before the lesson starts about how we represent molecules on paper. They should be comfortable with the scientific practice of developing and using models, as well as writing a CER paragraph, which stands for Claim, Evidence, and Reasoning. For more information on how to write a CER paragraph or what it is, linked on this site, there's a page with a document explaining the CER paragraph in full detail, and also a website that will take you through a CER paragraph and what its importance is in scientific writing. It's in the For Teachers section of this website. So when I do this lesson in my classroom, I purchase all the materials through Amazon. So you only just basically need film canisters and Alka Seltzer tablets. Alka Seltzer can obviously be bought also at any drugstore. The worksheet online is also required for this lesson, which again is posted to the For Teachers section of the website. Some suggestions I have for you if you're not feeling confident about how to run this. First, definitely, and I mentioned this before, set some standards for your class about how to develop models and how to make models. And you can even have a model drawn already showing how you'd like them to represent atoms. And it could be that everyone in the class is using the same shape or the same color, but you kind of need that in there so that when students look at each other's models, they have an understanding of what their peers are drawing. You also might want to differentiate between what water looks like at the molecular level and Alka Seltzer, and have that as a key up on the front so students know how to represent those two molecules. If you need to, during discussion as well, you can give students sentence starters to help them think about their models and think about the data from the rocket. So some examples are like, in data set 1 I noticed, in data set 2 I noticed, or I see this pattern because, just to help them have that conversation if your class isn't used to having partner and whole class conversations. For the second activity, when they're writing the claim, evidence, and reasoning, or CER paragraph, you definitely can help them out with that by having sentence starters or a model CER paragraph for them to look at. Again, resources for the CER paragraph can be found on the For Teachers section of the MIT Blossoms website for this lesson. Another thing you can do is intentionally group students so that they can have productive conversations. So put students together who they're comfortable with, or pair someone who enjoys classroom conversation with someone who struggles so they can help each other out. And also I would encourage circulating during this time to listen to student conversation to help construct the whole class discussion. So get a preview of what students are thinking. And so when you do construct whole class discussion, you already have students in mind you can call on to explain their ideas. For the final activity, activity 3, you should again do some intentional grouping. Maybe you want to keep the same partners, maybe you want to mix it up, because what they're doing now is applying what they learned to a new situation. You can circulate this during this time to help students design their optimal rocket. And you can also sort of challenge different groups depending on how you group them to think more deeply about the factors they just learned to apply to their rocket. Or you could differentiate by, if a student is struggling with this content, have them just consider one factor when they're designing their optimal rocket, versus students that need to be challenged more can consider 3 factors or 4 factors. Finally, just to be clear about how this is aligned to the next generation science standards, you may have noticed that I used really specific language throughout the video, and those language tools were related to the cross-cutting concepts embedded within the prompts. I've also included suggested prompts for you to use during your interaction with the students. And I included those because they're important and very intentional. Including vocabulary around the cross-cutting concepts in this lesson ensures that this lesson is truly 3-dimensional. For example, I asked the following questions at the beginning of the lesson, such as, what patterns did you observe? How are the structure of the rockets similar or different? What factors do you think cause the rockets to act this way? These prompts were purposely designed to structure student thinking towards specific aspects of this phenomenon, or in this case it was reaction rates. So this dimension provides a scaffold or extra help for teachers and students to organize their ideas around these scientific disciplines. So in addition to the cross-cutting concepts I used in this lesson, I also made sure students engaged in several science and engineering practices, such as asking questions and defining problems, developing and using models, analyzing and interpreting data, arguing from evidence, and designing solutions. So incorporating 3 dimensions of the next generation science standards in a purposeful way transforms this lesson from a traditional cookbook style lesson to a student-centered investigation. So hopefully students come away with more ownership of the concept due to their experience of discovery and design. My students really enjoyed this lesson. I hope your students do as well, and good luck.